Neptune was supposed to be quiet, far from the sun, frozen, predictable. Instead, it became one of the strangest planets we've ever discovered. A world where winds break records, storms appear without warning, and physics refuses to behave normally. Neptune sits at the edge of the solar system, the eighth planet from the sun, drifting nearly 4.5 billion kilometers away from the main source of energy that drives weather and activity on most worlds. At that distance, sunlight is faint and weak, barely capable of warming the upper atmosphere. From a simple perspective, scientists once assumed Neptune would be quiet, a frozen giant slowly losing the last traces of its internal warmth, a world long past its active phase. Everything about its position suggested a planet that should be calm, dark, and nearly asleep. Yet observations revealed something unexpected. Instead of behaving like a cold, inactive sphere, Neptune radiates more heat into space than it receives from the sun. This means energy is rising from deep within the planet, fueling atmospheric motion and maintaining a level of activity that defies early expectations. Rather than fading into stillness, Neptune shows signs of internal power, as if some engine inside continues to run long after it should have cooled. That discovery forced scientists to rethink what they believed about distant ice giants. The mystery deepens when we look at the planet's atmosphere. Despite receiving so little solar energy, Neptune displays dynamic weather patterns, fast-moving clouds, and violent storms that suggest a continuous supply of internal heat. Somewhere beneath layers of hydrogen, helium, and exotic ices, something is still releasing energy, enough to shape the behavior of the entire planet. The idea that a world so far from the sun could remain this active hints at processes we still do not fully understand. Processes that may involve deep convection, pressure-driven reactions, or residual heat from formation. And that raises a question that continues to challenge planetary science. Why hasn't Neptune cooled down like it should? Similar planets do not always behave this way, and comparisons with Uranus, which appears far less energetic, only make the puzzle more intriguing. Neptune seems to break expectations, holding onto an invisible source of power that keeps it alive in the darkness. The farther scientists look into this distant world, the more it feels like a planet refusing to follow the rules. On Earth, hurricanes are considered some of the most powerful forces in nature, driven by heat from warm oceans and fueled by sunlight. Their energy depends on temperature differences that create movement in the atmosphere, and even the strongest storms eventually weaken when they lose that energy source. Because of this, scientists once assumed that planets far from the sun, especially cold giants like Neptune, would have slow, quiet atmospheres. There simply didn't seem to be enough external energy available to create extreme weather. But Neptune shattered that expectation. Winds racing at more than 2,000 kilometers per hour have been observed in its atmosphere, speeds that exceed the speed of sound under certain conditions and far surpass anything seen on Earth. These are not occasional bursts. They are sustained atmospheric currents moving with extraordinary and consistency. The idea that such violent motion exists on a world receiving so little sunlight forces a fundamental question. Where does this energy come from? What makes the mystery even more fascinating is that Neptune should, in theory, be too cold and too distant to support this level of activity. Instead, the planet behaves like a giant atmospheric engine, with deep layers pushing energy upward and driving rapid circulation patterns. The atmosphere appears to be powered from within, as if unseen forces below the clouds are constantly feeding motion into the system. Scientists suspect internal heat and complex fluid dynamics play a role, but the full mechanism remains unclear. And that uncertainty is what makes Neptune so compelling. Something unseen is sustaining those impossible winds, something hidden beneath layers we cannot directly observe. The planet challenges our understanding of atmospheric physics by showing that sunlight is not the only driver of planetary weather. Each new observation suggests that Neptune is not a quiet, frozen giant at all, but a world where invisible energy continues to shape movement on a massive scale, reminding us that some of the most powerful processes in the universe operate far beyond our immediate view. When Voyager 2 passed Neptune in 1989, scientists were stunned to discover a massive atmospheric feature known as the Great Dark Spot, a storm so large it rivaled Earth in size. At first, researchers assumed it might behave like Jupiter's Great Red Spot, a storm that has lasted for centuries. The presence of such a colossal system suggested stability, a long-term structure anchored deep within Neptune's atmosphere. For a moment, It felt like scientists had uncovered a familiar pattern in an otherwise mysterious world. But years later, when powerful telescopes looked again, the great dark spot had disappeared completely. It didn't fade slowly. It was simply gone, replaced by new storms emerging in different regions of the planet. This shocked researchers because planetary storms were expected to persist, not vanish without a trace. Neptune seemed to be rewriting the rules, showing that its atmosphere was far more dynamic and unstable than anyone predicted. What makes this even more fascinating is the speed at which these changes occur. Neptune's atmosphere constantly shifts, with storms forming, drifting, merging, and dissolving in ways that suggest deep internal forces are at work. The planet's intense winds and internal heat likely drive these dramatic transformations, creating a system where balance is temporary and motion is constant. Instead of a stable pattern, Neptune behaves like a living climate engine that reinvents itself over time. Unlike Jupiter's long-lasting storms that feel almost permanent, Neptune's weather appears restless and unpredictable, almost alive in its behavior. Nothing stays stable for long, and every observation reveals a different face of the planet. This constant change challenges scientists to rethink how giant planets function, because Neptune proves that even in the coldest, darkest regions of the solar system, chaos and transformation can dominate the skies. Most planets in our solar system have magnetic fields that behave in a relatively predictable way, aligned with their rotation and centered near the planetary core. Earth is a good example. Its magnetic field emerges in a stable pattern that helps protect the planet from solar radiation. Neptune, however, breaks this expectation completely. Its magnetic field is tilted at a dramatic angle and shifted away from the center, creating a structure that looks distorted and unstable compared to other planetary magnetic systems. This strange configuration suggests that something very different is happening deep inside Neptune. Instead of a simple metallic core generating magnetism in a stable layer, scientists believe the planet may contain vast regions of superheated, electrically conductive fluids, possibly a mix of water, ammonia, and methane under immense pressure. In those extreme conditions, these materials behave in unusual ways, forming what some researchers describe as a massive, turbulent internal ocean capable of producing chaotic magnetic energy. Because the magnetic field is not centered, it wobbles and twists as Neptune rotates, creating a constantly shifting magnetosphere. This instability could have major consequences for the planet's upper atmosphere, influencing how charged particles move and how energy is distributed across its clouds. Rather than acting as a simple protective shield, Neptune's magnetic environment may be injecting additional complexity into the system, feeding turbulence instead of calming it. This leads to one of the most intriguing questions about the planet. Could the magnetic chaos below be connected to the violent atmosphere above? The link between internal structure and atmospheric behavior is still not fully understood, but Neptune hints that deep, invisible processes may be driving everything we see on the surface. If that connection proves true, the planet would not just be a cold, distant giant. It would be a world where unseen internal storms shape the skies in ways we are only beginning to understand. If you love exploring mysterious worlds and extreme planets, subscribe now. Because the farther we travel into space, the stranger it becomes. Deep inside Neptune, pressure reaches levels almost impossible to imagine. Methane, one of the gases present in its atmosphere, is squeezed so intensely that its molecules begin to break apart. When this happens, carbon atoms separate and reorganize under extreme forces. Scientists believe that in those crushing conditions, the carbon can crystallize into diamonds, transforming what was once gas into solid structures deep within the planet's interior. It's a process that sounds like science fiction, yet physics suggests it could be a natural consequence of Neptune's extreme environment. What makes this idea even more fascinating is the scale. We're not talking about small crystals forming in isolated pockets. Theoretically, enormous amounts of carbon could condense into diamond-like structures that slowly fall through layers of dense fluid and superheated material. Imagine entire regions of darkness where solid diamonds sink endlessly, pulled downward by gravity through a world that no spacecraft can directly observe. The deeper they travel, the more alien the environment becomes, hotter, denser, and more energetic. These falling crystals may not just be a curiosity. They could play a role in how the planet works. As the diamonds sink, they release gravitational energy, converting motion into heat. That heat might contribute to Neptune's mysterious internal warmth, a planet that radiates more energy than it receives from the sun despite being so far away. In other words, this diamond rain could be part of the hidden engine that keeps Neptune active, helping explain why its atmosphere remains dynamic instead of frozen and still. If this process is real, Neptune becomes more than just an icy giant at the edge of the solar system. It becomes a natural laboratory where extreme physics reshapes matter in ways we barely experience on Earth. A place where gas transforms into gemstones, where darkness hides constant motion, and where the laws of pressure and gravity create phenomena so strange they force us to rethink what planets can truly be. When scientists compare Neptune and Uranus, something immediately feels wrong. On paper, they should behave almost the same. Both are classified as ice giants, both formed in similar regions of the solar system, and both share comparable sizes and compositions. Yet when astronomers observe them closely, the differences become impossible to ignore. Neptune is active, turbulent, and energetic, while Uranus appears calm, muted, almost asleep. Two planetary siblings, but two completely different personalities. Neptune radiates significant internal heat and drives extreme winds that reach incredible speeds, while Uranus emits very little excess energy and shows far less atmospheric drama. This contrast challenges expectations because standard planetary models predict similar thermal behavior between worlds with similar mass and composition. It's as if Neptune still has a powerful engine running beneath its clouds, while Uranus lost or buried its own long ago. The question isn't just why Neptune is so active, it's why Uranus isn't. One leading idea points to ancient chaos during the early solar system. Some researchers believe Uranus may have suffered a massive collision that tilted its axis and possibly disrupted the way heat escapes from its interior. If its inner layers became locked, heat could remain trapped, leaving the planet unusually quiet on the outside. Neptune, on the other hand, might have avoided such a catastrophic rearrangement, allowing its internal energy to flow upward and fuel its violent atmosphere. But even this theory leaves gaps that scientists still struggle to fill. And that is what makes the comparison so fascinating. It refuses to fit neatly into our expectations. Two planets born under similar conditions ended up following radically different evolutionary paths, reminding us that planetary history is not predictable or uniform. Every time Neptune is compared with Uranus, the same conclusion emerges. We don't fully understand how these worlds work yet. Neptune doesn't just challenge theories. It exposes how much of the solar system's story is still missing. Neptune sends us a quiet but powerful warning about how limited our assumptions can be. From a distance, it appears calm, a smooth blue sphere floating peacefully in darkness. But the more scientists study it, the clearer it becomes that appearances are deceiving. Beneath that tranquil color lies an atmosphere driven by extreme winds, unpredictable storms, and internal energy we still cannot fully explain. If a planet that looks so serene can behave with such hidden intensity, then perhaps our first impressions of worlds beyond our solar system are often wrong. This becomes even more important when we consider that Neptune-like planets are incredibly common in the galaxy. Astronomers have discovered many exoplanets with similar sizes and compositions, suggesting that ice giants may be one of the most typical planetary types in the universe. Yet if Neptune itself challenges our models with unexpected heat, chaotic weather, and unusual internal dynamics, how many distant worlds are doing the same? Each discovery forces scientists to question whether our current theories are only describing part of the picture. The warning, then, is not about danger in a dramatic sense. It is about humility. Neptune reminds us that planets are not simple systems frozen in time. They evolve, shift, and hide layers of complexity beneath seemingly uniform surfaces. A calm blue appearance may conceal violent atmospheric engines, deep chemical transformations, or magnetic structures unlike anything we imagined. What we call stable might actually be temporary balance, and what looks quiet could be hiding constant motion far below the clouds. Perhaps the biggest lesson is this: the universe rarely follows the rules we expect. Ice giants may not be cold, inactive leftovers of planetary formation, but dynamic worlds with their own internal power and mysteries. Neptune stands as a reminder that the cosmos is full of surprises waiting behind beautiful illusions. And if one of the closest examples still confuses us, then the planets orbiting distant stars may be far stranger, and far more alive, than we are ready to imagine. Neptune should be silent. Instead, It roars through space with impossible winds and hidden energy. A distant world that breaks the rules we thought were universal. Subscribe for more cinematic space mysteries. Because every time we look deeper into the universe, we discover how little we truly know.